Okay, welcome everybody. In this video, we're going to discuss a little bit about the polar form of complex numbers. All right, so we've seen before that we can express a complex number in the XY plane. All right, so we can graph ordinary real numbers on a number line. We need a plane to plot or to visualize a complex number. All right, remember we can always write a complex number in this format where we have z is equal to a plus bi, or in this case we're writing it as x plus yi. All right, we treat that as one and the same as the ordered pair xy. All right, so when we go to plot a complex number, we're thinking about the complex number being associated to the ordered pair xy. So we got the Cartesian coordinates, or the rectangular coordinates sometimes called. All right, and we're going to think about converting that over to polar coordinates as we've seen in other places. So let's just review that a little bit here. Some of the old conversions, and just talk about those. They come from this picture that we've got drawn here, and we can just read off from the triangle. All right, I'm just going to draw and erase here. So for instance, looking at the angle theta being in the lower left corner, the adjacent side is x, the hypotenuse is r, and that would give us the first relationships that x is r, cosine of theta, pardon me, is x over r. If you multiply both sides of that equation by r, that identity by r, you would get the first of the polar coordinate conversions. And similar for sine. Sine is opposite over hypotenuse, which would be y over r. Multiplying by r to clear the fractions, we would get this conversion, that y is equal to r sine theta. All right, so those two together constitute one kind of pair of polar coordinate conversions that go together. All right, the other ones come from the Pythagorean theorem, and that is that x squared plus y squared, and just reading off this triangle, a squared plus b squared would equal c squared. X and y are playing the role of a and b. The hypotenuse is r. We get x squared plus y squared equals r squared. And then the opposite over the adjacent would be y over x. So that would then tell us that tangent of theta would be equal to y over x. So that pair underlined in red there goes together as well. All right, now what that's going to show us then is that we can express any complex number x plus yi in terms of r and theta. Now, to be clear here, r is standing for the radial length. We're thinking about a complex number. If that complex number is z, then the magnitude of that complex number is the same as that radial length. So in the formulas we're about to write down, that we just treat those two as one and the same. Some references you might see r, some references you might see magnitude of z of the complex number z written with the absolute value bars. So all we're going to do is just directly substitute in our complex number z. We're thinking about the x as x plus yi. Well, if we just put in from the polar coordinate conversion here, we're going to put in r times cosine of theta in for x, and then we're going to put r times sine of theta in for y, and then that's the imaginary component. All right, and we can also factor out r here from this. So another way to write this, we're going to see below, is that it's r times the quantity cosine of theta plus sine of theta times I. Sometimes the I is written after, like I've done it here. Other times you might see the I written in front of the sign. So that is the polar form of the complex number z. All right. All right, so we're going to be working with that a little bit, and I've got the next box we're going to see. It's got some of that summary there, so we can write down a complex number in what's called polar form. All right, and we're going to utilize Euler's formula, which is an important result. All right, so really what Euler's formula states is that, I'm going to write this kind of off to the side here. I'll write that in red. It states that e to the I theta is the same as cosine of theta, that complex number, e to the I theta is the same as this, plus I times sine of theta. So sometimes, again, you can write the sign in front of the I or the I in front of the sign, doesn't really matter. But all we're going to do is then up above here, what I wrote in blue, if we take that up here, then we could rewrite this expression then as r times the base e raised to the I theta. And that's the polar form. That's one version of the polar form. It's very convenient. So we've got kind of two versions of the polar form. Both are important to know. One of them expresses it in terms of cosine and sine. All right. The other one, which is very useful for raising complex numbers to exponents or to take various nth roots of complex numbers, is r e to the I theta. All right. So again, both are going to be utilized, but the second one turns out to be a little bit more useful. Okay. So let's get a little bit of practice with converting from one form to the other, or converting from polar form to rectangular form. All right, a couple of comments here. Addition and subtraction of complex numbers is really simple in rectangular coordinates or Cartesian coordinates. Some of the arithmetic operations like multiplication and division and powers, they're much harder in rectangular form or Cartesian form. They're much simpler in polar form, and especially when we write the complex number in the format where it's r e to the I theta. All right, so let's get a little bit of practice just with that format before we get to some of those powers. Okay, so I'm just going to rewrite a couple of these, and then we'll convert the other way. So this is kind of good practice, converting from polar form to rectangular form, and then we're going to go the other way from rectangular form or Cartesian form to polar form. So let's just take a look at a couple of these examples here. All right, so let's take just a look at how about number 29 that's listed here. This is from the Lippmann textbook. So again, we're just going to rewrite this. Again, we're going to express this the other way this time. So we're going to say, okay, if we've got r e to the I theta, we can rewrite this as r times the quantity cosine of theta, the angle theta. In this case, we're writing in radians, and then I times sine of the angle theta. All right, so that's what we're going to utilize here. So for 29, we're going to look at 3 e to the 2I, and we're going to rewrite this. Okay, so I think that this is likely a typo in there, and let's just assume that this exponent's not just 2i. Let's write that as I times 2 pi, just for the purposes of this example. So let's just assume we've got here I times 2 pi. So our angle theta in this case is 2 pi. All right, so what is that looking like then? So r is 3, so we're going to leave that as 3. Then we're going to have cosine of the angle, which is 2 pi, plus I times sine of our angle, which is 2 pi. Radians are 360 degrees. Now, sine of 2 pi is 0, so this is just going to completely wipe that out, and that's going to be able to let us rewrite this as 3 times, well, cosine of 2 pi is 1, so it's really 1 plus 0. So this is just the basic real number, just 3. All right, so it has a very kind of complicated expression in terms of 3e to the I times 2 pi power. All right, but it has a much simpler expression in rectangular coordinates. All right, let's do one more of these problems. How about we take a look at number 33? All right, so the one that's listed up there. So again, we're going to convert that from polar form. So it's 3e to the 5 pi over 4 I power, or you can put the I in the front there if you want. Again, the angle we're concerned about is theta being 5 pi over 4. So we convert this over to rectangular form. It's using Euler's formula, it's going to be 3. All right, that is your radial length, and that's going to be cosine of 5 pi over 4 plus I times sine of 5 pi over 4. Now these are common angles here, so we can put in the exact values. So we're going to have 3 times cosine of 5 pi over 4 is negative square root 2 over 2. And then we would have plus I times sine of that is square root 2 over 2. All right, so multiplying the 3 through the parentheses, we could rewrite this as negative 3 square root 2 over 2 plus 3 square root 2 over 2 times I. All right, let's look at a couple examples going the other way. So we converted some complex numbers in polar form to rectangular form. All right, a plus bi. Now let's go the other way and let's convert from a plus bi form to r e to the I theta form. All right, let's start with a couple of sort of straightforward ones or simple ones where we've got either a purely real number or a purely complex number. All right, so let's think about plotting those. Again, each one of these we can think about as, in this case, oops, not 0, but we can think about this first one here as 6, the complex number 6 plus 0i. For 37, this would be 0 plus negative 4i. Now keep in mind, we associate that with the ordered pair and respectively 0, negative 4, and the other one would be 6, comma 0. So think about plotting those down here in the XY plane. I've got one listed here. All right, we'd have, let's just ballpark them here. Here we've got, let's say that that's 6, comma 0. And then we'd have here on the imaginary axis 0, negative 4. Again, we always plot the real axis as the x-axis, the imaginary axis as the y-axis. Let's think about those points and then just write down the corresponding angles. So then what we want to think about is, I'm just going to draw this in here in red, thinking about this segment here, this length. What's that radial length, all right, for each one of these? So for this one, we're 6 units away from the origin for the first point. The other one, we're clearly 4 units away. So if I'm going to take the complex number 6 and write that in polar form, we've got to know what r is. So in this case, r is 6. Now it's going to be e to the I times theta power. Well, theta stands for the angle you make with the positive x-axis. In this case, that angle would be 0. Okay, that's one way to write that. Another way for us to do this would be, I did not put in my r value. I said r, I did not put in r. It would be 6 times e to the I times 0, or we could do 6 times any coterminal angle with 0. So we could also do 6 times e to the I 2 pi power, or 4 pi or 6 pi or 8 pi or any other angle that's coterminal with 0. Now, what is the angle coterminal with this value here? All right, that angle there is 270 degrees, or in terms of radians would be 3 pi over 2. So if we were going to take the complex number negative 4i, the purely imaginary number negative 4i, the radial length, it's 4 units away from 0, and that radial length we want to think about as positive. So if we're putting this in the form r e to the I theta, then r would be 4, and then theta would be, one way to recast this would be to rewrite this as 3 pi over 2. All right, likewise, we could rewrite this as, there's more than one way to write this down. Okay, we could use other angles. We could use negative pi over 2. So another acceptable way to do this would be e to the negative I to, pi over 2 power. That would be also equivalent. So as we've seen with computing ordered points in the XY plane, there's a unique set of rectangular coordinates, but there is infinitely many different polar coordinates for the same ordered pair, same point. Likewise for complex numbers, which we associate with points in the XY plane, in the rectangular coordinate plane, there are a unique set of rectangular coordinates, but there are infinitely many polar coordinate forms for that. All right, and each of them are just found by finding a coterminal angle to it. All right, let's do one more example for this recording. Let's take a look at number 41 that's listed here. So let's rewrite that complex number. So the complex number is negative 3 plus 3i. All right, so let's use our conversions here. Again, we're associating this with the ordered pair negative 3, 3. All right, so we're thinking about that as x and that as y. So we know that r squared is equal to x squared plus y squared. Substituting that in here, we would have negative 3 squared plus positive 3 squared. That would be 9 plus 9. That would be 18. All right, r squared would equal 18. So r itself would be the square root of 18. Okay, we can leave it as a square root of 18. We could square root factor by factor to get this as 3 times the square root of 2. All right, either one of those is fine. Okay, now we got to think about the angle. All right, now for the angle, remember tangent of theta is equal to y over x. So if we put in our y value and our x value, we get 3 divided by negative 3, which is negative 1. All right, now what we would want to do here is solve for the angle theta. So we would think about taking the inverse tangent. All right, To isolate the theta, we would take inverse tangent of each side to cancel the tangent out, which would be inverse tangent of -1. Now, if we compute that, we're going to get negative pi over 4. Okay, now this is where we got to be a little bit careful with polar coordinates. So that's not quite the angle we would want here. All right, now let's keep this in mind why that's the case. Okay, so again, the equation we ended up solving was tangent of theta is equal -1. One solution to that equation, yes, it is negative pi over 4, but tangent is a pi periodic function. So one solution, yes, is negative pi over 4. If I rotate by 180 degrees or pi radians, then another solution would be 3 pi over 4. And that's what the one we need, because our ordered pair is -3, 3, which is, for instance, right here on the terminal side of that angle. So we cannot use theta to be 3 pi over or negative pi over 4. We must recognize that we have to compensate by adding pi onto this. So the angle we actually need here is negative pi over 4 plus pi, which comes out to 3 pi over 4. Okay, so putting this together, then we would have our complex number -3 plus 3i can be rewritten as in the form r e to the I theta, with the value of r that we found, which was the square root of 18, which we could rewrite as 3 times the square root of 2, and then e to the I 3 pi over 4 power. All right, that's it for this recording.